I want to do a couple more little harder examples on improper integrals, and I kind of set this one up for you because we've done this integral before, and it's a pretty time-consuming integral, and I didn't want this video to be too long. And as I said, we've done this integral before. It requires integration by trigonometric substitution. So we're going from 0 to infinity, obviously improper, 1 over x squared plus 9, and obviously substitution wasn't going to work. So I started by rewriting it with a limit. The limit as b approaches infinity. Okay, and that integral comes out to be 1/3 the inverse tangent or arctangent of x over 3, and evaluating at b and 0. So, you know, as we now plug these values in, we have 1/3 the inverse tangent of b over 3 minus 1/3 the inverse tangent of 0 over 3, so just and we're still taking the limit as b approaches infinity. Well, this is, of course, is the point where we actually start looking at what would happen if we, plugged infinity in. And I know students that I have will always say, why do I even need this limit statement? I mean, does it really affect it? Can't I just do the antiderivative and then think about infinity? You really can. I'm just trying to give you the correct notation. Well, I pulled a graph of inverse tangent up. Let me pull this in for you. Inverse tangent looks like this. Okay. Of course, we know what tangent looks like. This is just rotated, and it has a limit as it goes to infinity of pi over 4, or pi over 2, excuse me. Okay, because that's the vertical asymptote of tangent. Okay, so I'm just going to put a little note in here. Its horizontal tangent is pi over 2, and of course negative pi over 2 on the other side, but we're going to positive infinity. So what we end up with here is pi over 2. Okay, that's what happens as tangent goes to infinity, inverse tangent. Of course, dividing by 3 doesn't matter. It's still going towards pi over 2. We have the 1/3 right here. Well, the other piece, what is the inverse tangent of 0? Well, it's 0. Okay, so we end up then with just minus 1/3 multiplied by 0. So the answer is just pi over 6. Okay, so we needed some knowledge of inverse tangent. This is kind of a big one. The AP exam's not going to ask you to do ones like this, but I thought it'd be kind of fun to look at one where we needed the inverse tangent graph. In this example, I wanted to show you, we get in this idea that we can evaluate the infinite bounds, but not the discontinuous types of impropers. You'll notice here we're going from 0 to 1. I've graphed this 1 over the square root of x squared. We have an infinite discontinuity here at the end. And a lot of people right away when they see that, they say, well, it's going to be divergent. It's not going to work, because a lot of them are that way. A lot of the discontinuous types of impropers are divergent, where a lot of the infinite bound types, you can find an answer. But I want to show you one where we can actually get an answer out of this. Let me rewrite. I'm going to do the limit as b approaches 0, and by rights we should say from the positive side, since of course we're looking at it from the positive side of 0. Integral from b to 1, and let me write this as x to the negative 1/2 dx. Okay. Well, the antiderivative, we raise the power to x to the 1/2, divide by the new power, so just 2. We're going to evaluate at 1 and b, and we're still taking the limit as b approaches 0 from the positive side. Well, of course, this, let me just write underneath it, this is just 2 square roots of x, right? I mean, that's what this is. So we plug in 1, we get 2 square roots of 1 minus 2 square roots of b, and we're doing the limit as b approaches 0 for the positive side. Well, this is just 2, and now we say, well, what if I actually plug 0 in? It's 0. So the area approaches has a limit of 2. And how this works, of course, is if you plugged in a really small decimal, 0.1, 0.01, 0.0001, the area is going to get closer and closer to 2. That's its limit. And again, I wanted to do this one because I've had students in the past just say, well, it's a discontinuous function, so it's obviously going to be divergent. It's not obvious. You still have to go through the work and check and make sure. It's certainly easier to look at infinite bounded improper integrals and get those to converge, but you do have to check.